Yeah, in this video, I'm going to discuss about the applications of the inductive effect under the chapter 4 of structural theory in organic chemistry. Um, in my previous video, I've already discussed about this inductive effect. It is nothing but the bond polarization involving the sigma electrons. Yes, if the sigma electrons are involved in the polarization, then that is called as an inductive effect. So let us look at the applications of inductive effect. So inductive effect can be used to explain the basicity of amines, acidity of carboxylic acids, and the stability of carbonium ions. So these three can be explained based on the inductive effect. Yes. Um, Before going to the basicity of amines, let's understand what are amines. See, for example, if you take ammonia, where ammonia is NH3, yes, um, ammonia, if you take ammonia here, if the hydrogen of this ammonia is replaced by an alkyl group or an aryl group. Aryl group is nothing but the derivative of an aromatic compound. If it contains a ring with a conjugated system, then that is called as an aryl group. If the H of ammonia is replaced by an alkyl or aryl group, then those are called as amines. So these are the derivatives of ammonia, where the hydrogen is replaced by an alkyl or the aryl group. So those are called as amines. So let's understand what are bases and what is the basicity. Yes, what are bases? The bases are, if you take the example of an amine here, this R in H2, where the nitrogen is containing the lone pair of electrons here, if it is able to donate the electrons or accept the protons, those are called as bases. So they are electron donors or proton acceptors are nothing but the bases. So this ammonia has a lone pair of electrons, or the derivative of ammonia, the amines has a nitrogen which can donate the lone pair. So it acts as a base. So the more it can donate the electrons, the more is the basicity. So the more is availability of the electrons, the more is the basicity. The basicity of amines depends on the availability of the electrons on the nitrogen. So let's understand the basicity of the amines based on the example given and write them in their increasing order of the basicities. If you take, for example, ammonia, methylamine, dimethylamine, and the chlorocompound of an amine, if you take this, let's understand first. If you take, yes, R and H2 here, this is amine. Yes. If this R group, for example, is let's understand the basicity of amines here. For example, if we take amine, so if the availability of electrons on this nitrogen is more, then it is more basic. So how this inductive effect will affect the basicity of amines? Let's see it. See, for example, if this R of NH2, if this R group is replaced, if suppose this is an plus I group like CH3 group, okay? If this is plus I group like CH3 group, we know that CH3 is plus I effect group, that means electron releasing group. It releases the electrons into the system, so which in turn will increases the electron availability of nitrogen. So this can donate the electrons easily now, which increases its basicity. On the other hand, if this R is minus I group like Cl, now this is electron withdrawing group. It will withdraw the electrons from the system towards it, which in turn will decreases the electron density on the nitrogen. So this will decrease the basicity. So overall, we can sum up like this. The plus I effect groups increases the basicity and the minus I effect groups decreases the basicity depending upon the availability of the electrons on the nitrogen. When you look at the example of ammonia and methylamine, dimethylamine and the chloro compound, we can see that dimethylamine there are two methyl groups which are plus I groups here. So it increases the electron availability on the nitrogen. So its electron availability is increased. So its basicity is increased because it can donate the electron pair easily now. But when in methylamine there is only one CH3 group, so its basicity is less when compared to that of this dimethylamine, and which is now this methylamine is more basic than ammonia because there is one methyl group. But when we come to this chloro derivative, this chlorine is electron withdrawing group here. So it will withdraw the electrons from the system. This will in turn withdraw the electrons from here, which in turn will decreases the electron availability of nitrogen. So this is less basic when compared to that of ammonia. So this all depends on the availability of the electrons on the nitrogen, which is directly proportional to the basicity. If electron availability is more, it's more basic. Yes. Now, when we look at this basicity of amines, primary, secondary, and tertiary, this is secondary, this is primary amine, and this is tertiary amine. So the basicity order is this. But the tertiary amine is expected to be more basic because there is availability of electrons is more on nitrogen because of 3 plus I groups here. But it is less when compared to that of the primary. This is because of the steric hindrance here. Sir, the group to come and attack here, for the other group, there is lot of hindrance because of these 3 methyl groups here. So because of this, the tertiary is less basic than primary, and then comes ammonia in the order. So secondary is more basic than primary, then comes tertiary, then comes ammonia. Yes. Now look at the acidity of carboxylic acids. So what are acids? The acids is exactly opposite to that of this bases. They are proton donors, the ability to give the protons. Give away the protons is the proton donors. If they're able to give the H plus ions more, it's more acidic. So let's look at this carboxylic acid RCOOH. On the hydrolysis, will give the carboxylate ion. The more it gives the protons, the more is the strength of the acid. So the acidity here depends upon the bond dissociation of OH. If the ease with which the dissociation, I mean, if it is easy for, if it's able to give away the H easily here, the more is the acidic. So the strength of the carboxylic acid depends on the ease of the dissociation of the OH bond. The greater the ease, the greater is the acidity. So when will this acidity be more? When will the bond dissociation will be easy? Let's understand this based on the example given here. So if the bond dissociation is easy, that means if we are able to dissociate the OH bond easily, then the more acidic it is. So for example, when we take the CH3 here instead of R, if it's replaced by CH3, which is plus I effect group, that means it will donate the electrons into the system. Then the availability of the electrons on the oxygen is more here. COOH, yes. Availability of the electrons on this oxygen is more. So the ease of dissociation is less here. It cannot dissociate easily. So this will decrease the acidity. This is just the opposite to that of the basicity here. So the plus I groups, for example, the CH3 group is an electron releasing group. It will release the electrons into the system, which in turn will increase the electron density on the oxygen, which will decrease the OH bond dissociation. So acidity is decreased. On the other hand, if there is minus I effect group, for example, the Cl instead of R, which will attract the electrons from the system, which in turn will decrease the electron density on the oxygen, which will increase the bond dissociation of the OH, which will increase the acidity. This is the opposite of the basicity again here. So the plus I effect groups decreases acidity. The minus I effect groups increases the acidity. This is because the plus I, repeat it, for example, the CH3 will release the electrons into the system, which in turn will increase the electron density on the oxygen. So the ease at which the OH bond is dissociated is less. So the acidity is decreasing here. On the other hand, if chlorine is there instead of this CH3, which is a minus I effect group, which will attract the electrons from the system, it will decrease the availability of the electrons on O, so the OH bond can be dissociated easily. So the acidity is more. Yes, just the opposite of the basicity. Yes. So plus I effect groups decreases the acidity and minus I groups increases the acidity higher. Yeah. Next is when we look at the examples here and try to write the acidities. We have taken formic acid, acetic acid, chloroacetic acid, and dichloroacetic acid. This chloro is minus I group here. And let's look at this order now. Yes. Next slide. If we take dichloroacetic acid, the Cl is minus I effect group. It will attract the electrons from the system. This in turn will try to draw the electrons from the system. So this will decrease the electron density on the oxygen. So it can, the bond dissociation is easy. So thus increases the acidity. If the bond dissociation of this OH is easy, that means it decreases the electron density at OH oxygen atom, and thereby OH bond dissociation increases and thereby increases the acidity. So dichloroacetic acid is more acidic than formic acid. When we come to the chloroacetic acid, there is only one electron withdrawing group here. So this is less acidic when compared to dichloro, but more acidic when compared to formic acid. When we come to acetic acid here, the CH3 is electron releasing group. This is plus I group. It is releasing the electrons into the system, so thereby increases the electron density on the oxygen atom. So the bond dissociation becomes difficult, thereby decreases the acidity. So it is less acidic when compared to that of formic acid. So the order is as shown below. Yes. Next one. So to sum up what I've said just now about the basicity and the acidity, yeah, let's look at this. in one sentence, the basicity of amines, if there are plus I groups in the system, it increases acidity because it increases the availability of the electrons in the system. If the electron availability is more on the nitrogen, it can donate the lone pair easily and thus increases the basicity. If minus I groups are there, it decreases the basicity because it decreases the availability of the electrons. But on the other hand, when we come to the acidity of carboxylic acids, if the plus I groups are there, then it will decrease the acidity. This is because plus I groups is there. This is because it will release the electrons into the system. So the bond dissociation becomes difficult. So of OH bond becomes difficult. So acidity is decreased. But if minus I groups like Cl group is there, it will withdraw the electrons from the system, thereby the availability of electrons is decreased, thereby the bond association becomes easy, so thereby increasing the acidity. Yes. Now coming to the stability of the carbonium ions here, what is a carbonium ion? Let's understand what is carbonium ion. A positively charged carbon species are called as carbonium ions. For example, CH3 plus or CH2, CH3 and so on. Right. Let's understand the stability and the order of this stability of these carbonium ions. This is a tertiary carbonium ion because 3 alkyl groups attached to this positively charged carbon. This is secondary, this is primary, and this is a methyl group. The tertiary is more stable because the 3CH3 groups attached to the central carbon positively charged carbon is stabilized because of the plus I effect of alkyl groups. So because of the plus I effect of this, it is releasing the electrons into the system, thereby the positive charge on the central atom is stabilized. So all of them share the positive charge, so it is stabilized. But in the second species, when we come to the secondary, only there are 2 alkyl groups to share this positive charge, the plus I effect groups. The positive charge here is shared by only 2 methyl groups here. So this is less stable when compared to that of the tertiary. Then comes primary. There is only 1 group here to share this positive charge. Then comes methyl. So tertiary is more stable. Tertiary carbocation is more stable than secondary, which in turn is more stable than primary. And then comes methyl in the order of the stability of these carbocations.